years ago, a king would send envoys with ships and things to different parts of the world and would ask them, bring me models of what you see there so that I could see what's going, how the things look like there. After this theorem, there is no need to send anybody anywhere because we know that no matter what the three-dimensional object is, it's constructed by using these 9 pieces, and this is how they look like. And now, so they managed to classify the three-dimensional manifolds, and now the four-dimensional manifolds is a big problem, as I told you. I mentioned this to somebody. That any conjecture how to classify the four-dimensional manifolds topologically or differentiably, which is more or less, topologically, was wildly untrue. No matter what type of classification conjecture you make, there are counterexamples, but such counterexamples, it's impossible to save the day in the end. I mean, wildly untrue. And the people don't know what to do. Of course, they have to employ things that they know from differential geometry, like the Ricci flow. So if you start with a metric on the four-dimensional manifold, compact and closed and blah, 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 you go to you solve the equation, you go to the limit, and you hope that the limit pieces will give types that you know. And then you will conclude something about the topological manifold. Keep in mind, this is all geometry. Right? They want to, the geometry is very hard to understand. And I think this was the idea in general, and asked him that. Even maybe it sounded a little bit rude. Was the Holy Grail in this? I mean, what problem are you solving? I mean, why? Are you entertaining us with what you proved lately, or is there something that the people fight for? And my understanding was that this is what the people want. They want to classify objects. And one of the classification methods is by using the Ricci flow. His answer was, well, it's too bold to expect that we can classify the things, right? The problem is much harder than that. But we want to do something in between here and there too. That's always like that. This is the research.
Is pretty strong. Keller.
Yeah, and what they can do is when they restrict the Ricci flow for a Keller manifold. Keller manifold, to have a Keller manifold, it's ask your advisor. Keller manifold, for him it's not interesting even, because if it is Keller, it's too big of a restriction on the manifold. Most of the manifolds are not Keller. Every algebraic one is Keller, complex algebraic one is Keller, but most of the manifolds are not. And the model of our four-dimensional world has to be Einstein manifold, but why should it be Keller? It's a huge restriction.
But even in the Keller case, it's not completely done.
It's not known, but what they can do is in that case, and what he said in the end of his talk was that actually they generalized something from algebraic geometry. I mean, they had a model already proven in algebraic geometry, and they showed that in the world of Keller manifolds you can do it, or a similar thing, reasonable generalization. So it's a very complicated. It's not. Of course, differential geometry, you have to solve differential equations. You want to construct an object, and you construct it by solving the differential equation. That's the way. And it's tough. It's very tough. I mean, I understand.
Professor, when you talked about trying to classify three manifolds, and you talked about piecing together certain things, I'm thinking, are they algebraic or differentiable?
No.
Differentiable?
Yeah.
Differentiable?
They are differentiable manifolds with
certain
very special metrics on them. So these are, we know how they look like.
Yeah, okay,
For example, they're hyperbolic, some of them are hyperbolic, so we know it's a quotient of the three-dimensional space.
I understand. Each piece will have, I guess, its own metric, like a a different signature on each piece.
Yeah.
Every metric has a signature. But
honestly, I'm not an expert in this area. So what I have read here and there, this is what I share with you. But
and so that's three folds, and that's the story basically, and then
This was the Riemann, the Poincare conjecture.
yeah.
For three, yeah.
Now for four manifolds, which unfortunately everything I'm doing is like 4n dimensional. You're saying that for that it's
Well, it
nearly
depends-
impossible to
depends
classify?
What kind of problem you are solving?
No.
Hypercouplet structure, so of course he needs 4n dimensions.
Yeah, but
Come on.
I know that.
It depends on
No,
what you are doing, what problem you are solving. If you want to classify the four-dimensional differentiable manifolds,
Because
Tom Lennes is an expert in this.
really, I need
does
to talk to
that,
him. Because apparently what I'm doing is a kind of change of variables formula for kind of what would end up being your paraquaternionic manifolds, and it's like a kind of change of variables Jacobian formula for it that you can put under integral signs, and he said that it would have implications to Morse theory, to the differential topology of the manifolds. And
No, I looked in some. You showed me something, some paper. It's a wild computation.
well, yeah, I'm trying to. I've gotten it a little better, and I'm doing it all complex because the authors do it real, and I don't know why. And maybe there's a reason, but I can't figure it out.
So
But
it was interesting. The talk was interesting, informative. They proved that conjecture, that the singularity